Okay, yep, just started the recording. Just speaking a little to do a volume check, both for people watching the recording later and just as people join as well. I hope you're doing okay. It's kind of a bright, sunshiny-ish day here. I am finishing up grading. Lag behind on homework sets, I know, so I'm like been finishing up like a question here, a question there when I get a pocket of time. Today will be one, tomorrow will be one. I've got an exam to grade for calculus, so a lot of grading this weekend is the big plan. get get as caught up as possible. On my end, I apologize. I think part of it is just figuring out how things are turned in and what's working for students and what's not, and if I clarify expectations in the future of like one PDF instead of several PDFs when turning in things, like there's a lot of little things I didn't think of to figure out, but hey, that's life. I have to deal with the timing of some things, and that's okay. But I hope you just kind of understand what's the deal and what's taking time a little bit in the process. But it's somehow like I guess the way I'm used to doing things, like I know how to do things in a way that's efficient, and here it's sort of like, I don't know, just do this, and then kind of after people have turned in things in, I'm like, oh yeah, that's gonna take me a lot of extra time I didn't think about. So yeah, I'll get better at it, or I'll just take what we have and just get faster at it. That's the other thing. So yeah. Okay, got 15, huh? 210. All right. Welcome back, folks. I need to find my mouse cursor again. There it is. And push that over there. Just reminders. Let's see. So, turn in homework 9 today. There's this additional clarification by email. I somehow kind of forgot about this, but then remembered this kind of moment in office hours. I just tend to avoid putting notation both directly before and after a comma. So even the way I wrote this here, at least on paper or whatever this is, I used a lot of space after the comma to try to clarify what's going on. Um, and then start homework 10. In fact, at the end of class today, I'm going to project homework 10 on screen so that you can see, oh yeah, I should really start homework 10. I really am going to try to encourage people to like not fall behind. I know like this is a weird time for me to suggest you create a habit, but the topics we're looking at are really involved, and I think the sooner you can start homework, the better things will go. Please be patient with yourself in this process. We are at, I think, what people consider the most difficult topic in the course. That said, please don't give up. Come to office hours, schedule an office hour by appointment. If you don't want to use data or bandwidth and you want to call the office phone number during office hours time, cool. If you want to set up by email, let's meet or let's do something, let's figure out something to do that's kind of lower bandwidth. Okay. Even an office hour by appointment can be done by phone call. I mean, we'll make I want to as challenging as all this is, make things work as much as possible. So I'm going to write down the first definition that's in my notes, but perhaps in just, I don't know, a slightly different fashion. Two sets A and B are equicardinal if there exists a bijection from A to B. I will just comment like we did yesterday that informally you can just say A and B, if you prefer this phrase, have the same cardinality. That's fine, right? And so, look, if you are presented two sets, they're described to you, and then you are asked to prove that the two sets are equicardinal. This is again where I don't want to keep reinventing the wheel. The text right after that first if, I mean, this if, it really operates like an if and only if, but if you need to prove equicardinal, then you need to prove that there exists. And so to prove that there exists, as we've heard all semester, really, right? Like you've got to make the thing, you've got to define a thing. So I hope you already saw examples of this yesterday. We're going to do more difficult examples today, actually way more difficult in some sense. But I just to make sure we're on the same page, and I don't want to make this a story of repeating all the things, but like the whole point is, I hope it does not come as a surprise based on the definition that to prove A and B are equicardinal. You got to do two things. So first step, you need to define a function. And I didn't even name the function up in the definition because the name of the function didn't matter, but I'll just include, I guess, an f here, right? A function f from A to B. So when defining the function, you need a domain, codomain, and rule. 2 out of 3, domain and codomain, I guess, are provided because you're supposed to, you're already told the two sets. It's just a matter of which order you want them in, which should be domain and which should be codomain is your kind of your call, whatever's easier for you. But you have to provide a rule. And providing a rule, this step 1, providing the rule is the hardest part. If you provide the wrong rule, step 2 doesn't work. Step 2 is to prove that this function f is bijective. So if you provide the wrong rule, then your function won't be bijective. If your function is not bijective, you can't prove it's bijective. Only functions that are bijective could be proved as being bijective. I'll just make this note, as I have in my notes here, that sometime at home you could work on this statement, prove that A is equicardinal to B. So the grammar here is just slightly different than in the definition up there. But this phrase, A is equicardinal to B, you can actually, if you'd like to, it's a good exercise in in some of the proofs things that we've already looked at. In fact, with functions, you could prove that this is an equivalence relation on sets. So like on all sets. So just it's a good little side exercise to try to make sure that everything's going okay. Today, what we're going to really do is look at, this is really related to all the cardinality stuff. So let me just get a couple definitions down and then we'll get going. We'll dive into the key example of the day. A set S is countable if S is finite, or S has the same cardinality as Z positive integers only. So it'll be convenient for us to just have the set of positive integers only instead of the set of all integers, and you'll see why kind of in a moment. And notice in this definition, it really is an or. I mean, that's the word, not and. If you put an and there, then with the modified definition with an and here, there's going to be no set that's countable at all. So that we don't want that. Okay, and then another sentence here, a set that is not countable is called, you could leave out the word called, I guess, if you want, is called uncountable. So let's note that both of the underlined new words, countable and uncountable, these are both, the note here is to say that these are both adjectives, right? These are adjectives for sets. So we have no business trying to say a countable implication, right? Like an implication is a proposition. You could never use the adjective that way. A countable equation, nope, doesn't work, right? So an equation actually happens to be if there's variables in an equation, I guess you have a predicate, right? So, but anyway, sorry, I'm off topic already. Let's not do that. One other quick definition before we dig into some examples is a set that is countable So let me pause already, right? If you have a set that is countable, then let me underline maybe in green back up here. One of those things has to happen, right? Either S is a finite set or S has the same cardinality as the set of all positive integers. So one of those things happens. If a set that is countable and infinite, so a set satisfying both of those properties. Now think about it. If a set is countable and infinite, up in the other definition where those two things are underlined in green, now that we are also including an and here and it's infinite, that means we're striking out the S is finite, right? So in the sets that we're describing in this new definition, it's the other condition that S has same cardinality as set of positive integers. Anyway, so let me finish this definition. This is called countably infinite. So you got to kind of put all the definitions we're seeing here to kind of all together. But in the end, a set that's countably infinite has to have the same cardinality as the set of positive integers, right? I mean, if you were going to prove that a set is countably infinite, you have to make a bijection in the. So let me scroll up just a little bit. You have to make a bijection where among A and B, one of them has to be the set of positive integers, and then the other has to be the set you're concerned with. And we will see examples of this today in a moment. Before doing that, let's dig into a couple tiny examples first. So let's look at. I'm going to define a set B. 2, 4, 6. There are 3 elements here, right? This set is finite. I didn't review that, but we did yesterday. Finite set, there exists a positive integer n such that B has exactly n elements. In this case, n is 3, right? So a finite set, look, it's an or up here. So that means, it's an or. So you only need one of the two, at least one condition satisfied. So not only is B finite, so B is also countable. So countable. So is B finite? Yes. Is B countable? Yes. C equals empty set. Okay, this is finite. There exists a non-negative integer that describes how many elements are in C. That non-negative integer here is 0. So countable again, right? Every finite set is countable. D, set of positive integers. This is not finite. But D has the same cardinality as Z greater than 0, right? Now you might say, well, of course it does. It's the same damn set. D and then set of positive integers, it's just 2 different notations for the same set. So D is countable. Are we okay with that last example? That D is countable? Right, because it's the other underlined green thing. S has the same cardinality as set of positive integers. We can also say, so since we have now a countable infinite set, we can also use the language, so D is countably infinite. I should comment, though, it's kind of maybe a little pedantic. This phrase, D has the same cardinality as set of positive integers, that actually should have a proof. I mean, you might say, well, look, a set having the same cardinality as itself should just be obvious, and I put obvious in quotes as I say this. But the thing is, we have a definition. So technically, in order to even claim this, I think you should work on proving it. I'll just hint at sort of the thing you should do is you should define a function, which I'll call little f, from D to D, right? So to prove that D has the same cardinality as D, there needs to be a bijective function using D as the domain and D as the codomain. The rule for this function, how about the input is just the output? This function is known as the identity function, right? In kind of other areas of math, or in this area of math as well. Okay, the function where the output is just whatever the input was. So this function ends up showing, in all cases, even if you had a different set here, right? If you had, instead of D as domain and codomain, if you had whatever, H as domain and codomain, you know, the identity function, the function whose rule is output is just copy the input. This always is the thing that shows a set is equicardinal to itself. So even that little thingy there, you know, technically speaking, requires some bit of proof. Okay, theorem. The set E, and I'm just going to describe the set as granola as possible. So, I mean, there's other fancier ways to write the set, but I'm just going to kind of right now go with set starting with 2, 4, 6, 8, 10, 12, ... follow the pattern. This is countable. So I want you to work on the proof here, right? So first of all, it's going to help if we just, to get started, even though E is written in that format, staring at this, let's go backward. I mean, I know we've done kind of the other way around. But let's write E in this format that's helpful for proof. So placeholder variable J. There exists K in integers such that J is equal to 2K. Right? So I'd like you to then take a moment and, you know, let's start the sentence. We define a function f from, so look, to be countable here, think about it, the set E isn't finite, right? So we're going to have to construct a bijection. We have to build a bijection where one of the sets is set of positive integers and then the other set is E. Now you could swap these two if you want, but I guess I will just give you this hint, this general tip, that sticking the set of positive integers in the domain spot is usually much easier to deal with because you know those, like E here, you know, I mean, E is up here and these numbers are easy enough to deal with, but like in general, your set E or whatever you have might not be numbers, might not be filled with numbers, it might be filled with other things. So it's kind of much easier typically to just use as the domain the set of positive integers. So we'll with rule. So I'd like you to think about it. You know what? I'll wait for a moment, right? I want you to think about. We've got the set of numbers. Let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, da 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 da. And over here you've got the set 2, 4, 6, 8, 10, 12, da da da. Think about, can you make a rule so that based on the rule, if a good rule is put in place here, then you end up with a function that is going to be bijective and could be proved to be bijective. I just want everybody to have a moment. Okay, yeah, cool. Or write it, that's fine too. Yeah, so f of x equals 2x, right? And so then what would need to be done here, and it looks a lot like one we did yesterday, so I'll leave it to you to do this at home because we have bigger fish to fry today, but I would ask you to take this function with this rule. It's not the only one that works, but it's probably the nicest of the rules that work. Other rules that would work have to be piecewise. They'd be kind of awful. Let me just, what the hell? I'll just tell you one that, well, let me finish this and say at home, you should prove that f is injective and f is surjective, right? So I'll leave that to you because we've got kind of bigger things to do. And just if you're curious, like what do I mean by other functions that are going to work? You're going to hate this function, but I'm going to just mention it just to say there's other options. So Lindsay's example here was 1 gets mapped to 2 and 2 gets mapped to 4. Basically, each input gets mapped to its double. And I'm basically going to copy that work with one little exception. My function g is going to be piecewise. And all I'm going to do is I'm going to use the same formula 2x if x is greater than or equal to 3. However, for the first two inputs of 1 and 2, if x is equal to 1, if x is equal to 2, normally, I mean, Lindsay's rule over here was going to assign a 2, then a 4. I'm just going to swap them. A 4, then a 2. That's it. I know it's kind of cheap, but hey, it works, right? At least I hope it feels like it should work. If 1 maps to 4 and 2 maps to 2, and then beyond that, 3, 4, 5, and so on, and those 3 and beyond, those inputs all just map to their doubles again. That should work. As strange as it is. I will just make this general comment that defining your own function is challenging, right? So defining the rule of your function is challenging. So if you're struggling to do it, you're not alone. What I'm saying is that's probably what I'm going to get a lot of questions on in office hours, and I'm expecting that. That said, today my goal is to not just say things and have you go, where the hell did that come from? My goal today is to try to let you in on some of the insight. Like, how am I thinking about it? How am I coming up with the rule? I want you to see as much of that as possible. And so my just general hint related to this is draw pictures, Venn diagrams. There's an upcoming response where even if it's talking about people getting sandwiches and so on, like there's a lot of ideas that may be helpful, like the infinite hotel room, infinite buses. There's like all kinds of ideas that I want you to take with you, and I want you to work on translating what all these different scenarios that don't sound anything alike actually have to do with the next theorem. So here we go. Let A and B be countably infinite sets which are disjoint. So disjoint means, right, that the two sets don't share anything in common. The intersection is defined. It's just that the intersection is the empty set. Okay. Then A union B is countable. So you have A is a countably infinite set. You have B is a countably infinite set. These two sets don't share any elements in common. Just for simplicity's sake right now, right? These two sets don't share anything in common. And then we are going to prove that when you union together the sets, so take both buckets and dump them into one bucket, that this new set that you get, the union, is going to be countable. Now, of course, this union, it's not going to be a finite set, right? How could you start with an infinite set and then another infinite set that don't share anything in common, dump everything together and get a finite set magically? You can see that that's not going to happen. So how's countable going to happen? Countable, remember, was an or. The only way it's going to happen is if you have countably infinite. So in fact, this question could have been basically worded the same if it ended with then A union B is countably infinite. So let's dig into a proof. Now, the fact that A is countably infinite means that there exists a bijection. Right? To be countably infinite, A has to have the same cardinality as a set of positive integers. So positive integers as domain tends to be more helpful. Codomain A. Right? So there exists a function f from set of positive integers to A. But B is also countably infinite, so there exists a bijection f from positive integers to B. Wait a second. Do you see this kind of problem, right? I shouldn't probably use the same function name here. So let's switch that to a G. Okay with this? So if our goal is to prove that A union B is countable, then what we want to show is that there exists a bijection. There exists bijection. I guess let's name it a new letter, little h. With, again, it's more helpful to use domain as set of positive integers, and now the codomain should be A union B. Right? That's what we want. So here, to define the function, we need a domain. Well, we'll use that set of positive integers. We need codomain. We'll use A union B, but we need a rule. Rule for H. That's going to be the hard part. We're doing okay so far here, maybe. So what I'd like to do is everything inside this box is not part of the proof. I want you to see where the ideas are coming from. So call this scratch work if you want to, but I want you to think of, I'm going to skip a space down here because I'm going to write in this space in just a moment later. But like informally, just super informally, let's just say that the elements of capital A are little a1, a2, a3. These a1, a2, a3 might not even be numbers, right? It's just A is a set. A is a countably infinite set. Maybe A is, so A sub 1 might not be a number. Let's not think that it's a number. But there's a first, I know that sets are not normally ordered, and they certainly aren't, but for a moment, let's just pretend that they are. And what I'm really trying to get at, if you want to know what I mean by A sub 1, I mean that's actually the value of f at input 1. So whatever f of 1 is, right? So if you go back here, it makes sense. If you have something in the domain, set of positive integers, you apply f, you should get an element of A. And then this A sub 2 is just my sort of casual notation to mean what was really f of 2, right? And A sub 3, that's f of 3. And written in this form, comma separated like here, there's this sort of, what's the word? There's the possibility of like the same element being written twice. We just don't notice it, but like the whole point of having a function that's bijective is every element of A should be written once and only once in this list, and there are these dots here because we can't write them. We don't have the time to write them all down. Same deal. B, I'm going to skip a line and have here there's a B1, B2, B3, B4, and so on. And by B1, what I literally actually mean is G of 1. By B2, I mean G2 is what B sub 2 is equal to. And G of 3 and so on. So if you think about it, like informally speaking, the idea of what it means for there to exist this bijection F, it means you could tell if the set A was filled with people who could listen to your command, it's like you're telling them, hey, everybody get in a line. Somebody should be standing first in line, somebody should be standing second in line, and so on. And same thing with B here. But now we need to have everybody form a line together. But there are these two infinite lines. So what do you need to do? You got to merge, right? So you're going to do this thing where it's like, okay, then A1 first, then B1 next, and then A2, then B2, then A3, then B3, then A4, then B4. I call this kind of like a zigzag kind of thing that's going on. Right? So we're looking for a way to sequence all the people. So there's a way to sequence the elements of A union B. Now this is just in a picture. So well then what? Like what do we do with this? How do we actually develop a rule? Here's how. I want to remind you of something from homework 2. So in homework 2, you had to deal with a sequence that looked like this. So 1, 2, 3, 4, 5, 6, that just was the subscript for which element in the sequence you're dealing with. And then we had, I'd like you to recall, we had a situation like in homework 2, you had a sequence that looked like this: 1, 1, 2, 2, 3, 3, 4, 4. And I want to remind you that you could look at the key if you want, but you were asked to provide a piecewise formula for this. And the easier part is actually dealing with when n was an even, like 2, 4, 6, 8, because then your output, 1, 2, 3, 4, you just had to divide by 2. So n over 2 if n even. And n, when n is odd, this was a little harder, but it wasn't too bad. If n is odd, do you recall you had to do like is it an n plus 1 over 2 or an n minus 1 over 2? One of those. I think it's n plus 1 over 2. But I want you to see how that's related to what we're going to do right now. So right now, if we have n, now we have h of n. See, we're trying to figure out what the rule is. So if I just call the input variable, it's a placeholder variable anyway. Instead of calling it x, I'm going to call it n. So same deal, right? Like this, 1, 2, 3, 4, 5, 6, 7, 8. So over here, this means h of 1, but I don't want to just write h of 1. I like h of 1 meaning the first, what's the first output of this function h, right? And then h of, over here, this spot, h of 2. Well, take a look. I'm actually going to just copy paste this. Sorry for that little bit of technological, oh, I missed one. Okay, I'll just write in this. Now this is not good enough quite like this, but this is the idea. Check this out. The thing is, if the blue are these things, or that's the, let me try over. Let's do this. If the blue is like this one right here, and the two, those are the inputs to F, and then the reds over here are the inputs to G. Take a look. We kind of have to do some kind of clever composition. What we actually have here is F of 1, G of 1, F of 2, G of 2. Whoops, that should have been in parenthesis. F of 3, G of 3, F of 4, G of 4. I mean, if you look back over on this side, that's what's being described, right? If you zigzag, look, it's A1, which is just a fancy name for F of 1. So it's F of 1, followed by G of 1, followed by F of 2, followed by G of 2. And in this way, wouldn't we end up getting every element of A union B once and only once? So it looks like what we need to have going on is something like look, the blue inputs suggest that we need something like a f of n plus 1 over 2. So compare the blue over here for homework 2. The blue numbers 1, 2, 3, 4. Now we have to f each of those, right? And then the red 1, 2, 3, 4. The red 1, 2, 3, 4 that appear right here and there and there and there. It's not just 1, 2, 3, 4. You apply to those red 1, 2, 3, 4, we have to apply G. So it looks like we're going to have like a G of n over 2 kind of thing going on. I'm going to pause for a moment, see how we're doing. All of this is to suggest, yeah, I should put this comment here. None of any of the things in the box here are part of the proof. Not part of the proof. I mean, these are the thoughts you should have when working on a proof like this, but it shouldn't be presented in your proof. This is all like scratch work. So then let us define a function h from set of positive integers to A union B by the rule h of x or n. Let's go with n. Why not? H of n, piecewise, should be f of n plus 1 over 2 if n is odd, and g of n over 2 if n is even. Now you kind of see the role of why there was this kind of random problem in homework 2, I hope. Okay, so we've defined a function now, right? H, we have a domain, codomain, and finally a rule, even though the rule is piecewise. Now our goal is to prove, we want to show H is bijective. Before proving H is bijective, I want to address anything that I can say about the rule. I think typing is not maybe the goal here, I think this is kind of a place where if you've got something you want to say or comment, or like, can I think of it this way? Maybe you want to unmute, and so that we can kind of verbally discuss this, because this one's a little different, huh? Make sure we're okay. Just wait for a little longer, just in case the timing of things going back and forth on the internet here. Shall we prove that H is bijective so that you get more examples of proofs of function proving injective and surjective? All right, let's do this. So I'm gonna, yeah, I've got, I think, enough space here. So let's first prove, to prove H is surjective, remember, surjective is both injective and surjective. The definitions start with a for all. It's just for all and what. But remember, surjective is about everything in the codomain is really an output. So here's your codomain up there. I circled it just now at the top, A union B. So to prove, let's let, and I tend to use Y a lot for outputs, you know, because I think of still X's and Y's back from an algebra class. So let little y come from A union B arbitrary. So we're allowing the reader of this proof to pick any element they want from A union B, from the set A union B, and we need to show that this is truly an output. So we want to show there exists an X in the domain, which was a set of positive integers, such that H of X, using our rule that's given here, right, that this is going to equal Y. That's what we want to show. Now here's the thing. If Y is in A union B, then we know Y is in A or Y is in B. Right? Remember, a union is really an or. Now what? Cases, right? You see an or, whenever you see that or, if this or statement is true, you got to go, that smells like proof by cases. All right, proof by cases. So case one. So it's either that y is in A or y is in B, right? So let's go with y is in A. So let's suppose that we got this situation. So in fact, I'll include the word as I have in my notes here. Say that y is in A. Okay, so the reader picked something from A union B, and one option is they pick something from A. So since f, recall from earlier, f was a function from positive integers to A, since this function is surjective, by the way, the function f was bijective, but the key point is that I want to use is right now f is surjective. And so we're going to use that this f is surjective. So that means that there exists a C in positive integers such that f of C equals Y. Right? So this, we're using surjective. Here, please recall that the definition of surjective was it's a for all blah in A. So we're using a for all. To use a for all, you need an element in A, and we have one. It's called Y. So when you use that f is surjective, you get there exists an input that you can feed into f so that you really achieve getting Y as an output. Now I'd like to let x equal 2c minus 1. I'm going to leave out a little bit. I'm going to ask you to kind of work on a couple things. So I want you to note, and this, you know, that this number, okay, it feels quite clear that it should be an integer. That if c is a positive integer, that x is an integer, but why is x a positive integer requires just a little more work. But I want to leave. We've got bigger fish to fry right now, and because x is odd. Also here, it's not, I mean, it's probably fairly obvious to us, but I'm skipping the actual proof in that 2 times integer minus 1 does not technically make the definition of odd, but we've got bigger things to look at, so I'm leaving that out right now. So let's just kind of go with, based on how this is written, 2c minus 1. We were really hoping for 2 times integer plus 1, but that can be fixed with a little proof on the side. But since you have an odd, take a look at what happens. H of x, The point is, if we go with x is odd, what should h of x be? Well, look up here at our rule. And at our rule, for an odd input, we're supposed to follow this piece. Not the bottom piece, but the top piece. So we'll follow that. We'll just plug in for every n an x, and we'll have f of x plus 1 over 2. See what I did here was I copied what's there. We had to follow, because x was odd, right? X was odd. I just replaced all the n's with x's. And then, well, let's see what happens. Okay, let's f of replace the x with 2c minus 1. And then there was still a plus 1 in the numerator that I still have to copy over 2. This is f of 2c over 2 equals f of c. And f of c from just a moment ago is y. So cool. We have defined an x that in this case, in case 1, we're not done, but in case 1, we found the input for h that achieves the output y. Case 2 is actually easier than case 1, just by a little bit. So case 2, the only other possibility is y is in b, right? Because one of these two things up here had to happen. Either y was in a or y was in b. So what happens if y is in b? So since the function g from earlier, from positive integers to b, is surjective. Did I use a new variable here? I did. I could have reused a c because it's a new paragraph, but let's use a d as I have in my notes. There exists a positive integer d such that g of d is equal to y, right? So now we're applying what it meant for g to be surjective. The definition of surjective, again, starts with a for all, in this case for all whatever in b. So we're not trying to prove g is surjective. We know g is surjective. To use this for all in b, we need something in b, and we have it. It's called little y. And so that means, the fact that g is surjective means that there should be an input for g. That input to g is called a d, and when you apply the function g to the input d, you get the output y. And now what we're going to do is let x equal d over 2. Let x equal 2d. Yeah? Yep, yes, let's do that. So, by the way, if d is a positive integer, then how I defined x, it should be, here it requires even less work to notice that it's a positive integer, right? You start with a positive integer, multiply by 2, you should have a positive integer. And because x is even, we kind of this time see it more directly, like as an application of the definition of even, right? 2 times a positive integer, or more generally 2 times an integer. So then let's take a look at what happens when you compute h of x now. Now it's still just at the top of the screen. When you have even as your input to h, right? Up at the top, my input is called n. My input to h is called n. But if the input to h is even, you need to follow the second piece. You need to follow so we'll have g. Let's switch this back here color-wise. G of x over 2. It's just what our rule earlier told us we need to do, and then you can replace the x in the numerator with the 2d that we defined just a moment ago, and have 2d over still 2, cancel the 2, so you have g of d, and g of d we already said was y. So cool, we have, in both cases here, we have, in case 1, we reached h of x is equal to y, and in case 2, we reached h of x is equal to y. We defined an x that made that happen, so we have now in both cases proved that there exists an x in positive integers such that h of x is equal to y. That concludes proving that h is surjective. In fact, let me just write the sentence here just to make sure. So in both cases, we just proved that there exists a positive integer x such that h of x is equal to y. So h is surjective. How are we feeling so far? Comments on the proof of surjective? Questions on the proof of surjective? Anything anybody want to say? Maybe just a people want to type into the box or something like, I'm good, I want to move on to the proof of injective. I want to see kind of how we're doing. Let's do a proof of injective. Okay, I just copied the rule from earlier just because I think it'll, yeah, just so that we don't have to keep scrolling too far back in order to see what's going on is all. So to prove, I'm trying to see if anybody commented. I don't see one. So to prove that H is injective, recall that the definition of injective starts with two. This is a double for all on the domain set, though. So we should, to prove a double for all, we should allow the reader to pick two things from the domain, arbitrary. So I'll follow the notation I have, like the letter choice I have in my notes. Little p and little q belong to the domain. It's up here for reference. Be arbitrary. You could optionally write the words be arbitrary or not. The point is we don't get to control what it is. And then think about what we want to show, right? Now we want to prove if the outputs are the same, the inputs are the same. Right? That's just the next part. It's an implication. So to prove the implication, we should suppose the outputs are the same. The outputs of H anyway are the same. So we should suppose H of P is equal to H of Q, and we want to show P is equal to Q, right? Here's the thing. I just want to point out, or I want you to notice, since P is a positive integer, and same with Q, so P is odd or even. We're gonna just kind of go with, yeah, every positive integer either has to be odd or even. It's not both and not neither, right? And then also Q is odd or even. So this is going to create four cases for us. What I'd like to do is, so it's a mix and match, right? Because we know that one of these two facts occur. Either P is odd or even, and either Q is odd or even. So we actually had a proof that you had to do for homework in a kind of different situation where you dealt with an and of ors. So I'd like to, as case one, look at the situation of, let's say P is even and Q is even. That's one of four possibilities right now. So recall we had assumed up here H of P equals H of Q. So H of P equals H of Q becomes, now look, if P right there is even, that's the input to H. We've got to follow this piece down here, right? Whenever you're in, because it's a piecewise function, and if the input is even, we've got to follow the bottom piece right now. So the equation that we have, the left side, H of P becomes G, let's switch this, becomes G of P over 2. And the right side, which said H of Q, we'll just write that as instead G of Q over 2. Now, here's the thing. I want you to recall that G was injective. Remember, G is injective. Since G is injective, way at the beginning we said G was bijective. So bijective was both injective and surjective. And then let's think about what injective means. And we could do this super formally, but I'm going to be a slightly informal just so that we don't overdo it right now. But injective, remember, we're trying to prove H is injective. We're right now trying to use G as injective. Injective meant if the outputs are the same, the inputs are the same. And take a look what we got here. The outputs are the same, right? G of a thing equals G of a thing. So if the outputs are the same, we're applying modus ponens, right? So we've got then, since G is injective, and we have this statement over here about outputs being the same, it's because we were actually dealing with the same input. So P over 2 is equal to Q over 2. And then take that equation, multiply both sides by 2, and you get P is equal to Q. That's what we wanted to show. So we're done with 1 out of 4 cases here. Case 2, let's do P is odd. Oh, sorry, P is odd and Q is odd. So the equation that we had to assume, remember I supposed this before breaking into cases out of convenience. So we still have h of p equals h of q. And so this h of p equals h of q thing that we already assumed before going into the individual cases, this now becomes, well, look, if p and q are both odd, we got to follow the top piece here, don't we? Right? The input to h is odd. So this becomes f of, keep doing that, becomes f of p plus 1, was it plus 1? Yeah, f of p plus 1 over 2 equals f of q plus 1 over 2. But remember that f is injective, right? And injective was if you know the outputs are the same, it's because you actually had the same inputs. Even if the inputs don't look the same, they actually are the same. So we are going to equate the inputs. P plus 1 over 2 is equal to Q plus 1 over 2. And then take that equation, multiply both sides by 2. Now we're doing like algebra, right? Like before calculus kind of algebra here. And multiply by 2 on both sides, you get P plus 1 equals Q plus 1. And then subtract 1 on both sides, and you get P equals Q, which again was what we needed, right? We had to always get to this goal. If you don't get to your goal you want to show, your P equals Q, then we haven't done anything. We haven't finished the case. Case 3, let's do P is even and Q is odd. Now here's the funny thing about this. So I'm going to look at, we still have this equation up there, right? H of P equals H of Q, but take a look. H of P, so since you have P is even, you've got to follow the bottom piece over here, and you're going to get G of P over 2. Now, I want you to recall that the codomain of G was B, so this is an element of B. And the other side of the equation, you had H of Q. That was H of Q. By the way, Q's odd, so you got to follow. I'll try to scroll up just one moment here. For the odd input to H, we've got to follow the F formula. So we'll have F of Q plus 1 over 2, but please recall that the codomain of F was A, right? So if you feed in an input that's valid into F, you should get an output that's an element of A. Thoughts? Reactions? What do you think? Why did I bring up these weird things, these sort of strange facts of we had to assume this equation that's still circled in the upper right, H of P is supposed to equal H of Q, but H of
P can not equal H of Q because it was already said that A and B are disjoint.
Right, it was said that A and B are disjoint, right? So yeah, right, and then this came in a text format as well. So the thing that we assumed in the first place, it seemed like we had 4 cases, but this case is actually impossible, right? So this is impossible. So H of P equals H of Q actually is impossible here, right? Is impossible because A intersect B, I don't want to say is undefined, that's not right to say, but we said at the beginning that the result of intersecting these two sets should be the empty set. And then case 4, I'll skip it. Let's just write down what the case hypothesis is. So it should be the only missing combination of situations. Once we write this situation down, we will have covered all our possibilities. Is P is odd and Q is even. I'll leave it to you. The argument is almost the same as case 3. So I want, I'll leave you to think about it a little bit, but you should basically, again, talk about something about impossible happening. So initially it seemed like there were 4 cases, but it turns out that 2 out of the 4 cases are impossible. Of the 2 cases that are possible, we needed to reach the conclusion of P equals Q, and you'll notice at the end of case 1 we did, and at the end of case 2 we did. So by a proof, using a proof by cases, 4 cases with, yeah, I've got a sentence that should help clarify. Not that you have to write a sentence this way, but I think for in class it's helpful to, 2 of the 4 cases are possible. And we showed the statement, what injective looks like there for all p, q in set of positive integers. If h of p equals h of q, then p equals q. Okay, so and then the other 2 cases were impossible, right? So, so we prove what we need to do. So h is injective. We have h is surjective from the previous page. We have h is injective here. This box says we have now completed the proof. This is a good time to take some questions, I guess. It's kind of involved at first, right? It takes a little getting used to. I would like to project, I don't know if that's the right word, present at least. Zoom in here. Oh, that was a little too much zoom. This is the homework that's due next Thursday. So take a look at question 1. So I did put in blue some I didn't initially have these comments in here, but I just little hints and this kind of thing, just like with the clarification document for the homework due today. But you'll see here this question 1, question 2, question 3. Those are all just they don't deal with the cardinality stuff in questions 1, 2, and 3. If you take a look, there's stuff about preimage, there's stuff about image, there's stuff about composition and injective and surjective in question 3. So all of those things are actually kind of questions that could have been on the homework, the last homework, because it was all about just function stuff, and we talked about all the things up to last Thursday. Monday and Tuesday were just meant to kind of talk about the things that are more challenging. The new thingies here that relate to cardinality things, having same cardinality, you'll notice it's question 4. And now question 5, I'll read it out to you because I want you to think about how the proof we just did might be very applicable, or at least a lot of the ideas might be. So if you have 3 sets, A, B, and C, they're pairwise disjoint, meaning A intersect B is empty and B intersect C is empty and A intersect C is empty. You take any 2 of the sets and you intersect them, there's nothing in common. And if A is countably infinite and B is countably infinite and C is countably infinite, then when you union all 3 sets together, you should get something countably infinite, right? So think about how you might prove that, and I also try to provide some hint as to like the whole reason of doing some sequency thing, piecewise sequence formula in homeworks 1 and 2, and then later on in homework 8, it was all to build up to this question. So I think I'll call it because maybe I'll see you in office hours in about an hour.